Recording has started.
All right, welcome back everyone. So today is the last lecture for the ECE 3030, and we will take this opportunity to review the final exam materials. And first of all, this is a guideline we already posted under the canvas. And let's go through the guideline one by one. So first, the final exam dates are scheduled to be December 2nd, Wednesday, to December 3rd, Thursday. So it's from noon to noon. And this is 24-hour take-home exam. So we have two sections for 3030. So the section A and B will be synchronized. That means we're going to use the same exam material and the same grading policy. You are expected to complete the exam on your own and obey the academic rules as usual. Today we are going to have a virtual review of the final exam materials, and I will also hold the virtual office hour tomorrow, 11 to 12, and also the week after, 11 to 12, on Wednesday. This is right before the exam starts, in case you have the last minute questions. So the final exam will be cumulative and cover the materials from lecture 1 to 19, excluding the materials on the lecture 20, which is the advanced CMOS and the industry trend. The expected length of the actual hours needed for the final exam is about 2 hours. So we have similar length as the previous midterm exams. The partition of the final exam materials before the first midterm will be roughly 15%. Between the first midterm and the second midterm will be about 25%. And then after second midterm will be 60%. So you can see here the focus will be the materials after the second midterm. That means lecture 15, CMOS scaling, and then lecture 16 to lecture 19 on the memories. The format will be similar as before, true or false questions followed by a few questions on the calculation or the diagram. And similar as before, we will post the questions under the exam folder, and then you will need to download that, and then you should complete the test, and then upload the scanned PDF as your solutions. Late submission is subject to the penalty. If you have any good reason that you cannot make the final exam on time, you must notify me by email before the exam starts. Requests submitted late may not be accepted. And finally, the final letter grade expectation. If you weight the total of all the assignments after we include the final exams grading as well, if your total is above 85, you will probably get A. Of course, we may fine-tune this cutoff line subject to the distribution of the final exam grades. But this is a tentative target if you want to reach A, and we will decide the other cutoff lines like B, C, D according to the distribution later. So, any questions about those guidelines here? Alright, then we're going to go over the materials for the final exam. And this is the tips how to succeed in final exam. So here we list the topics of the ECE 3030 from lecture 1 to 19. So here is an outline of the major topics we have gone through in the 3030. And let's have a quick review. First, we talk about the resistor and interconnects for the integrated circuits. And then we talk about the semiconductor physics, so basically the silicon's properties. For example, the bond model, we talk about the doping, the concept of doping, how to introduce additional electrons and holes in the silicon. And then we introduce the band model. So this is the energy band diagram. And this is very important because we are going to use this band diagram to describe the device structures in the following lectures, like the p-n junction, the MOS cap, MOSFET. We can use band diagram to illustrate how those devices work. And then the carrier statistics. So here basically how to calculate the electrons or the hole's density given the doping density. And then the parameters like the relative distance between the Fermi level and the conduction band edge EC or the valence band edge EV. And then carrier transport. So this is how those carriers move in the silicon. There are two mechanisms. One is drift, that is under the external electric field. And the other one is the diffusion. This is when the concentration of the carriers differ in different regions. Then the carriers from the higher concentration region will diffuse to the lower concentration region. So here we care about the density of the carrier and the velocity of the carrier. This is because the current eventually is determined by how many electrons or holes are there and how fast they move. So that's why we care about those two carrier properties. And then we talk about the device structures or the building blocks for the MOSFET. First one is the p-n junction. This is the junction between your source and the body, or the drain to the body. So those are the p-n junctions. So in the MOSFET, those p-n junctions should be reversed, biased, to avoid the large current across the p-n junction in the MOSFET. Because we want the MOSFET current to be conducted only at the surface after the channel is formed or after the inversion of the carriers. So this p-n junction is not what we want in the current conduction. But this p-n junction is important to build the MOSFET structure because we rely on the barrier between the source to the channel to control how many electrons or holes that can move over the barrier into the channel. So this p-n junction is a building block for the MOSFET structure and understand the IV characteristics of the p-n junction as well as the band diagram of the p-n junction. And then we have the MOS cap. So this is the MOSFET without the source and the drain. So if you only look at the MOS structure from the metal gate to the oxide insulator to the channel semiconductor, then we have this MOS structure. And essentially this is a capacitor. And for the capacitor, we talk about the electrostatics. So basically we talk about how the channel is formed or how the surface of the silicon is inverted. And this can determine the threshold voltage. So the threshold voltage has an equation to calculate the number for the threshold voltage. And then here we talk about the band diagram perpendicular to the channel, that is from the metal to the metal gate to the silicon channel, MOS. And then we have the Mosfet IV characteristics, including the subthreshold. So here we talk about the ideal square law IV characteristics. So there are three regions, like the cutoff, which is also the subthreshold region, and the triode or the linear region, or the saturation region. So have the respective equations for those regions. And for the subthreshold, on the lecture 10, it's important because it determines the standby leakage current that eventually determines the standby power of the digital circuits. And then we talk about the Cmos inverter. So we need to understand the operation principle and the VTC, voltage transfer curve, and the noise margin. And then we talk about the delay of the inverter. So we have the high to low transition, low to high transition. Then how fast is this transition? And we have two methods to calculate the delay. One is the average current. The other one is the RC equivalence. And then we talk about energy and power. So there are two kinds of energy. The first one is the dynamic energy or the active energy. So that is the charging and discharging of the inverter driving a capacitor load when the input is switching from 1 to 0 or 0 to 1. So the energy is a CVDD square in 1 clock cycle. And then the dynamic power will be this energy multiplied by the frequency and the activity factor. And then we have the standby leakage power. That is when the input is static. We don't do any computation there, but still you are consuming the power because the subthreshold leakage currents, as we discussed earlier. And then the last two topics, which are focus of this final exam. The first one is the Daniel scaling rule. This is lecture 15. So here we talk about the scaling trend from one technology generation to the next technology generation. And we have some assumptions on how those parameters would scale. And we have the constant field scaling, where we assume the dimensions of the transistor scale in proportional to the voltage scaling. So the field is a constant, and under that assumption, we will have some conclusions, such as the clock frequency can improve and the power density will remain in the scaling. Power density is defined as dynamic power divided by the chip area. And then we also have the constant voltage scaling, where the dimensions scale, but the voltage keeps the same. So under this assumption, then the power density will increase in the next generation. So we are going to discuss more later when we refer to the scaling table. And then we talk about the memory in the computer system. And there is a memory hierarchy with different kinds of memories in different levels of the hierarchy because of the trade-off between the memory capacity and the access speed. Closer to the processor, we want faster memory, but typically faster memory has smaller capacity. That's why we have this SRAM based cache, and even within the cache, we have level 1, level 2, level 3. So SRAM cache is on chip, and then we have DRAM, which is off chip. So here this chip refers to the microprocessor's chip. And then the DRAM is the off chip, that is for the main memory. And then we have the flash eventually as a storage, like the solid state drive SSD. So those are the major topics we covered in the 3030, and hopefully this can be a foundation for the hardware used in the computer system. Any questions so far? Then let's talk about the abilities you are expected to have for the final exam. So here, the blue part is from the first meter. And the first one is to calculate the resistivity of the interconnect metals such as aluminum and copper. And then be able to calculate the electron hole density given the parameters such as the Fermi level, relative positions respect to the EC and EV, and then understand there is an NP product which is regardless of the doping. So NP always equals to Ni squared. Ni is the intrinsic carrier density. That one only depends on the temperature. And then be able to draw the band diagram of the intrinsic N-type and P-type semiconductor given the doping density, and be able to label those parameters and the relative distance in the energy band diagram. And understand the mechanism of the drift and diffusion currents. And those two are not independent. The drift gives you the mobility, and then the diffusion will have the diffusion constants. So this mu and d has a relationship according to this Einstein relationship. And then understand the unidirectional behavior of the current flow in a p-n junction. So basically, the current can only flow from P to N in the p-n junction, and the reverse current is very small in the p-n junction. And understand the p-n junction's band diagram in the forward bias and reverse bias. And then for the Mosfet structure, we can derive the threshold voltage. And the definition of the threshold voltage actually means the density of the minority carrier at the surface of the silicon becomes the same as the density of the majority carrier at the bulk. So if it's Nmos, the substrate is p-type, then you have the substrate hole density. And then the threshold voltage is the volume where the surface of the silicon changes from the p-type to n-type. And the n-type gives you the electron density, and that electron density is the same as the hole density that is at the bulk of the silicon. So this is one definition of the threshold voltage. In other words, this also means at the threshold voltage, the band bending at the silicon surface, or we call surface potential, is this 2 phi b, and phi b is the distance between the intrinsic Fermi level and the Fermi level. And then we have an equation to calculate the threshold voltage and also the maximum depletion width when you reach the threshold voltage. And those equations tell you that the threshold voltage or the maximum depletion width depend on the parameters like doping density, dielectric constant, and the oxide thickness, and temperature, and so on. and then be able to draw and analyze the band diagram of a MOS structure. And in the lecture, we talk about the N-type MOSFET. But you should be able to do the P-type as well, because the N-type and P-type will be opposite to each other. You apply positive voltage to turn on the Nmos to create the channel with electrons. That means you are going to apply negative voltage, gate voltage, to the P-type MOSFET to invert the channel from the N-type to P-type. So be able to draw the band diagram for the MOS structure from the gate to the channel direction. So this is one direction. The other direction is along the channel direction. That means from the source to the drain. So also we have the N-type and P-type, Nmos and Pmos. So you should be able to draw the band diagram from the source to the drain. So basically we will have two PN junctions back to back. So you have a built-in barrier between the source to the channel. And understand how those band diagram will change when we apply the gate voltage or the drain voltage. So again, for all the energy band diagram, this is a general rule. If you apply positive voltage to any terminal, that terminal's band will be pushed down. If you apply negative voltage to any terminal, that terminal's band diagram will push up. So this is a general rule for drawing the band diagram. So any questions? And then determine the MOSFET operation region, like those three regions, cutoff or subthreshold, and triode or linear, and then saturation. So the boundary between the linear and saturation will be determined by the VGS minus VT compared to the VDS. So always check this condition before you apply the equations for the current, because you have to choose either the linear equation or the saturation equation. So here, those equations, as we required in this course, you only need to use the square law model. That is the first order IV equations. Next, the saturation current will be half mu COX W over L VGS minus VT squared. So this is the square law model. And then based on those models, actually you can draw the ID versus VGS plot or ID versus VDS plot. And from those two plots, you can determine the VD set, that is the boundary between the linear region and the saturation region. And also you can determine the threshold voltage from those plots. And then understand the saturation current will not saturate if we consider the channel length modulation effect. So this is the second order effect. Unless we tell you to consider this, then you don't need to include this into the calculation of your current. But qualitatively, if we ask you why the saturation current no longer saturates in the saturation region, you need to refer to this channel length modulation effect. And then understand the definition of the on-state current and off-state current. So I on is defined when the gate voltage equals to the drain voltage equals to VDD. And the off current is when the gate voltage is 0, but the drain voltage is VDD. So here if you plot the log scale of the drain current versus VGS, you should be able to identify the I on and I off from that plot. So basically that plot also gives you the subthreshold slope. And we know there is a lower bound limit for the subthreshold slope that is equal or larger than 60 millivolt per decade. So this means if we want to reduce the current by 1 decade n times, we need to reduce the gate voltage by 60 millivolts at least. So this is a physical limit for the MOSFET subthreshold operation. And then understand the differences between Nmos and Pmos. So everything is reversed in the Nmos and Pmos. So to make it easier, we suggest that when you look at the Pmos, always take the absolute values of the VGS, VDS. So if you, and also the threshold voltage. So if you always use absolute values, then you can use the same equations as in the Nmos. And then understand the basic operation of the Cmos inverter and draw this VTC, voltage transfer curve, that is output voltage versus input voltage. And then understand the definition of the noise margin and the VM voltage, which is defined when the input equals to the output voltage. And then understand the matched condition for the Cmos inverter. This is important because under this matched condition, the noise margin high and noise margin low should be the same. And also the high to low transition, low to high transition speed will be the same. So basically, the Cmos inverter is symmetric in the operation, like no matter your input is 1 or 0, then it should be symmetric. And then understand how the VTC will shift under the unmatched condition. So if it's unmatched, then depending on the relative strength of the Nmos and Pmos, we say that if the Nmos is stronger than the Pmos, stronger, for example, the Nmos W over L, mu N W over Ln, larger than mu P W over Lp. This means Nmos is stronger. Then the VTC will shift to the left. If the Pmos is stronger, the VTC will shift to the right. This is essentially that due to the fact that Nmos is for pull down. So Nmos is responsible for pull down the output. So like the high to low transition, you need to use Nmos parameters. And the low to high transition, then the Pmos is responsible for the pull up of the output. So this is needed when you calculate the delay for the Cmos inverter, either in the average, using the average current or using the RC equivalence. You have to use Nmos parameters for pull down high to low transition TPHL, and then Pmos for the TPLH. And then the dynamic energy in one clock cycle is CVDD square, and dynamic power given the clock frequency is CVDD square times F. And we also need to times alpha, which is the input activity. That is the percentage that the input is switching. So not every cycle your input will switch. So the probability or the percentage of the switching is this alpha activity factor. And understand this dynamic power is due to the charging and discharging of the capacitor load, and this is caused by the short circuit current from the VDD to ground when you have the switching of the inputs. And then the static leakage power is when the input is static. And this is due to the non-zero off-state leakage current, I off. This is the exact reason why your smartphone is still consuming your battery when it's in the sleep mode, because of this static leakage. So any questions? Alright, then the last part, the red part, is the material after second meter. So that will be the focus of the final exam. So lecture 15 is on the Cmos scaling, and we talk about the standard scaling rule. And we have two special cases. One is called the constant field scaling, and one is called the constant voltage scaling. And between that, we have the generalized scaling scenario. So let's look at the constant field scaling first. The assumptions are that the dimensions of the transistor scale in proportional to the voltage scale. So the field, electric field, is voltage divided by the dimension. That will be constant. So under this assumption, you will reach the conclusion that the power density remains the same in the next generation. Power density is the dynamic power of the circuit divided by the area of the circuit. But the clock frequency can be increased because the delay of the circuit will reduce under this assumption. And then in the constant voltage scaling, so in this case the dimensions still scale, but the voltage does not scale. Voltage remains the same. So under this assumption, you will reach the conclusion that the power density will increase. So this is actually what happened in the past few decades. Sometimes it's under the constant field scaling, and sometimes it's under the constant voltage scaling. But overall, the power density of the chip has increased because we cannot keep the constant field scaling always. Sometimes we have to keep the voltage the same. Why is that? We can have a very simple estimation here. So think about the 1980s. The transistor node is like a micrometer scale, and today it's about 10 nanometer. So from 1 micrometer to 10 nanometer, the scaling factor is 100 times. But the voltage cannot scale by 100 times. At 1980s, the power supply is about 5 volts. If you scale by 100 times, that means today the power supply will be 50 millivolts. But this is not true today. The power supply is still like 600 millivolts or 700 millivolts. It's not 50 millivolts. You can see that the voltage cannot keep the same rate as the dimension scaling. Therefore, the power density has increased. So the reason why we cannot scale the voltage the same rate as the dimension, it actually is because the subthreshold slope we discussed earlier. The subthreshold slope here we say 60 millivolts per decade. This is a limit. So if you want to maintain the on-off ratio at least 5 orders of magnitude, your transistor needs to turn on and off, right? So there is a ratio of the current. If it's at least 5 decades, that means the threshold voltage needs to be at least 300 millivolts. Therefore, your power supply must be larger than the threshold voltage to turn on the transistor. Your power supply must be larger than that. So in practice, today is like 600 millivolts, 700 millivolts, and that's why you cannot have the power supply down to like 50 millivolts. So this is the scaling in practice. But here we have two special cases. One is under the constant field, one is under the constant voltage. We will talk about this in more details later when we review the table that we summarize the scaling trend. Any questions? And then understand why there are different technologies for the memory a hierarchy. Essentially, this is due to the trade-off between the memory capacity and the access speed. Closer to the processor, we need faster memory, but faster memory typically has smaller capacity. And this is also true even within the cache. We have level 1, level 2, level 3. All of them are SRAM and memories. But the difference is that closer to the processor, like level 1, we have to use larger transistor size, like W/L of those SRAM transistors, to charge and discharge faster. But you use larger transistors, then given the same chip area, the capacity of the L1 cache will be smaller. So there's a fundamental trade-off there. And then understand the difference between the volatile memory and non-volatile memory. So volatile memory, like the SRAM, DRAM, after the power is removed, then the data is gone. Non-volatile memory is like the flash. When you remove the power supply, your data is still there. This is for the long-term storage. And then be able to calculate the access latency in the memory hierarchy using the recursive equation. So to calculate the level 1 cache latency, you have to start from the level 3 and then do backward calculation. And then for the SRAM operation, understand the principle. SRAM is made of 6 transistors. You have a cross-coupled latch, cross-coupled inverters in the middle, and then you have 2 passgate transistors to connect the storage nodes in the middle with the bitline bar. Then understand the voltage schemes for hold, read, and write operations. And for the DRAM, understand its principle is 1 transistor, 1 capacitor. So the capacitor stores the charge. If you have the charge there, you can represent 1. If you don't have charge there, you have 0. And then the bit line is pre-charged to be half VDD before you turn on the word line for readouts. So be able to calculate the sense margin, that is the voltage change on the bit line after you turn on the word line. Depending on the data pattern you store there, if you store 1, then the bit line will increase the voltage by delta V. If you store 0 there, then the bit line will decrease the voltage by delta V. So this delta V is the sense margin, and there is an equation to calculate this sense margin. And then understand why DRAM needs refresh. So basically, DRAM's capacitor will leak over time. The charge cannot be stored there forever due to the leakage current, for example, the subthreshold current through the access transistor. Then before your data is gone, then you have to refresh that. So the refresh is done by the read operation, because when you read, you will automatically recover or write back the data. And this refresh needs to be done within certain time interval. and in practice, typically 64 milliseconds. You have to go to the original location of the data and read it every 64 milliseconds. And then understand the percentage of the time that you spent on the refresh. Because out of those, let's say within the 64 milliseconds, you need to spend some time to do the refresh, and other time you can do the regular read or write operations. So understand how to calculate the percentage of the refresh in the time window. And then for the flash, we have the floating gate transistor, and understand the principle there. So we inject electrons into the floating gate, and this is the program state. Program state will have higher threshold voltage. Or we can remove the electrons from the floating gate, and this is erased state. An erased state will have lower threshold voltage. This is like a single level cell operation, just 1 bit per cell. But we can have multi-bit per cell by controlling how much amount of electrons inject to the floating gate. Therefore, we can have multi-level threshold voltages. If we can have 4 levels threshold voltage, then we can encode 2-bit data. Or if we can have 8 levels of the threshold voltage, then we can have 3-bit data. So this is one method to increase the integration density. So basically, one floating gate transistor can store multi-bit data. And another way to increase the integration density is to build the 3D structure. So we have the 3D NAND. That is to build the transistor vertically. So on the same two-dimensional space, we can stack multiple floating gate transistor vertically. So they all share the same two-dimensional space. Therefore, their equivalent area will be reduced by the number of layers you can integrate. Alright, so any questions here? Okay, so here are some tips. So nothing is beyond the lecture materials. And practice the sample exam, and we have done that last week. If you haven't done that, please review the recorded lecture last week. And then redo your homework and review the lecture examples. And you need a real calculator, but the key equations and the parameters will be provided to the appendix of the exam papers. Pay attention to the true or false question. There will be penalty if your answer is incorrect. So the best strategy is leaving it blank if you are uncertain about it. And finally, very important, to get partial credit, write down the appropriate equations first, and then do the numerical calculation. As you see, the grading policy before in the midterms, we are going to apply half of the credit to the appropriate equations, and then half of the credit to the final numerical values. So any questions? And let's quickly go over the key equations you may need for the final exam. So this is a combination of the equations that you used for the first meter and second meter, and a few new equations for the final. So I will skip the discussions of the equations used in the previous 2 tests. I will only focus on the new materials here. And actually, we don't have many new equations. in the last part of the course. So here, the first one is for the scaling, and we have this table that summarizes the generalized scaling rule. And here I can guarantee you that you may use this table for your final exam. So you want to be familiar with this. So here, if alpha equals to 1, it is constant field scaling. So here we see that the device dimensions will scale by the factor of x. And then if the alpha is 1, the voltage here will also scale by 1 over x. So this is a constant field scaling. So if you use a constant field scaling, then you can derive all the following metrics, like the electric field in the device and the capacitance of the node, which is approximated as a gate capacitance, and then the current through the transistor, and then the circuit delay, for example, one inverter's delay, and then the power dissipation per circuit. This is the dynamic power of the inverter. And then the circuit density, or in other words, is 1 over the circuit area. So if you use the power dissipation and the area, then you can get the P over A, that is the power density. So here, this is a summary of the conclusions. For example, if the alpha is 1, this is constant field scaling, and then you can reach the conclusion that the circuit delay will be 1 over x, because alpha is 1. So the delay will also scale. That means the maximum frequency is 1 over delay will increase. And then the power density will be 1, because in this case alpha is 1. But in another special case, when the alpha equals to x, so here alpha equals to x, this is like 1. So this is voltage. That means constant voltage scaling. So if alpha equals to x, then you can reach the conclusions. Eventually, you will see the power density will be alpha cube. And alpha is the same as x. X can be a number like 1.4, for example. Then this alpha cube will be larger than 1. And the alpha can be arbitrary number between those two special cases. Then that will be the generalized scaling rule. So you want to get familiar with this table and then be able to apply this table to the actual equation, actual problems. And then we talk about the latency analysis for the memory hierarchy, and this is a recursive equation. So here the perceived access time, big Ti, of a certain level depends on first the small Ti, that is the technology intrinsic access time of this level, plus the miss rate, Mi, multiplied by the perceived time of the next level. This is because when you miss the data, you have to look for it from the next level. So this is a recursive equation. You have to do it from level 3 to level 2 to level 1. And then for the SRAM design, we have the rate margin that is affected by this beta ratio. So basically, the W over L of the pull-down transistor needs to be larger than the W over L of the pass-gate transistor, because we need pull-down to be stronger than the pass-gate. And this needs to be larger than 1. And for the write, we care about this gamma ratio. That is W over L of the PU, pull up, over the W over L of the PG. We need the PG to be stronger than the pull up. But we need to notice that the pass gate is Nmos, pull up is Pmos. So even the W over L are the same, the Nmos is naturally stronger than the Pmos. So this one, when you have the equal or smaller than 1, you will satisfy the condition. And for the DRAM design, we have the sense margin. This is the voltage difference when you turn on the bit line. When you turn on the word line, how would the bit line change? So the delta V is given by 1 over 1 plus CB over CS. CB is the total bit line capacitance. CS is the DRAM cell capacitance, and then multiplied by the half VDD. So you can see that to make sure you have a large sense margin, then you want CB over CS to be small, or in other words, you want small bit line capacitance, a large cell capacitance. So this is the equation for the delta V in the DRAM sense margin. I think that's all for the equations. You don't have too many new equations. So that means you have to understand the concepts of those lectures in great details. So any questions here? If not, I think that's all for the review. And finally, I would like to thank you, all of you, for being cooperative in this semester. I know it's uneasy for everyone. And I believe that the CIOS, the teaching evaluation and feedback system is open. So I would encourage you to spend a few minutes to finish that, because I really appreciate that you can give me some constructive feedback to improve this 30/30 for the future semesters. So please take a few minutes and complete that. All right, then I think I am done here today, and I wish everybody a safe Thanksgiving, and then you can have a review of your final in the final before the final exam, and hopefully everyone performs well in the final exam. All right, thank you all of you. Bye bye.